Good evening and welcome to tonight's STEM Cafe, the physics of the Olympics. Thank you for joining me this evening. Tonight, two of our NIU particle physicists, Professors Dr. Mike Eads and Dr. Jahred Adelman, will discuss the physics behind the Summer Olympics. And it can all be understood without using any complicated mathematics. Dr. Eads and Dr. Adelman both have been speakers at our STEM Cafes before, so many of you already know that we're going to have a fun evening. You'll never watch the Olympics quite the same again. If you haven't done so already, please participate in our poll this evening. We will provide the results later in this program. I'm Dr. Judy Diamond, organizer of the STEM Cafes for the past 9 years and your host for this evening. STEM Cafes are brought to you by NIU STEAM and the Center for P20 Engagement at Northern Illinois University. NIU STEAM refers to science, technology, engineering, the arts, and math. We want to thank Bayer Fund and Thermo Fisher Scientific for making it possible for us to offer this STEM Cafe tonight free of charge. STEM Cafes are fun, casual gatherings where adults can eat, drink, and chat with STEM professionals about hot topics and the latest research. We currently hold our STEM Cafes, we usually hold our STEM Cafes in restaurants and look forward to getting back to those restaurants. In fact, we will be in person in Sugar Grove at the Open Range Southwest Grill on August 12th, a Thursday, for our annual stargazing event. For those that would prefer to attend virtually, we will be live streaming the event. Food will be available from 6:30 to 8:30, and our speakers will speak from 7 to 9, and we will observe the skies from 9 to 10:30. It will be a rain or shine event. We ask that you register for either in person or for the virtual event, whichever you prefer. We need to give the restaurant a heads up with the numbers so they can be prepared. So that's why we would appreciate it if you would also register if you're coming in person. Two of our speakers will speak virtually from NASA's Goddard Space Flight Center, and we are proud to say that they are NIU alum graduates. And two of our speakers are from Argonne National Laboratory. Also, our NIU STEAM instructor will be there to tell us all about the skies, and keep your fingers crossed, I think we're actually going to have moon rocks there from NASA. So it should be a fun evening. So tonight, you will need to provide your own favorite snacks, drinks, and carryouts. In the meantime, our partner restaurant, Fatty's Pub and Grill, we'll be offering a 10% discount if you order anything from them and say that you attended this evening. So thanks to the generosity of our patrons, we are able to offer this STEM Cafe free of charge. Please consider making a donation so we can continue to provide engaging programs like this one. Any donation is appreciated, small or large. The link to donate is go.niu.edu/give-NIU-STEAM. By the way, thanks to those who very generously contributed to Huskies United 2021 for STEMfest. Your contribution will help us keep STEMfest innovative, exciting, and free for the community participants of all ages. Be sure to save that date for STEMfest, October 23rd. During the month of October and leading up to STEMfest, we will have STEM Cafes every week and offer other offerings for families during those weeks. For those of you that have not attended our STEM Cafes, our format for this evening is as follows. Our speakers will talk for approximately an hour, and then during that talk and following the talk, you can put your questions or comments into the Q&A. We prefer that you use the Q&A rather than chat because we're going to leave the chat for any other concerns that you have during the evening. Also, we're using the chat to put our link for giving and for the survey, and possibly for the results of their poll. So we are going to use that for that purpose. So we appreciate it if you put them in the Q&A. Anyway, we will answer those questions after both speakers have spoken, and we will end at 8 p.m. If you experience any difficulty hearing during this evening, you can control your own volume, and it's usually located in the lower left-hand corner of your screen, so you can adjust that to your liking. This cafe will be recorded. It will be posted on our website, as the past cafes have been, in a week or two following the event, as we need to make sure that we have closed captions so everyone has it accessible to them. We welcome your feedback, and if you're interested in providing feedback or making a suggestion, we'd really appreciate it. The link will be in the chat if it's not already there. And or you can always contact me with my email, jdymond@niu.edu. And by the way, many of our STEM cafes have been generated from the audience. So let's get started with tonight's virtual STEM cafe. The physics of the Olympics. Again, you may write your questions in the Q&A during the talks, and we will answer them following. So according to Dr. Eads, a big part of physics is understanding moving objects. In the Olympics, there are many moving objects. Knowing some basic physics principles, such as forces and energy, can help to explain why athletes do the things they do in the various Olympic events. Physics is all around us and is what we all use to understand the world and our interactions with it. We can use some basic physics principles such as force and momentum and energy to describe all of these things. Newton's laws help to explain a sprinter's stance, why there's a lot of spring in a diving board, why divers and gymnasts change their body positions to spin while they are in the air. Our first speaker, Dr. Mike Edes, is an associate professor in the Department of Physics and director of Physics and Chemistry teacher licensure programs. He earned his PhD and his master's degree from Northern Illinois University in experimental particle physics, based on his research at the D0 experiment, one of the two large collider experiments at the Fermi Lab proton-antiproton collider. He did his postdoctoral research at the University of Nebraska, which was based at Fermi Lab, working on both the D0 experiment and the compact muon solenoid experiment at the CERN Large Hadron Collider. He earned his BS at Northern Illinois University as well in physics and physics education, and spent a short time as a high school physics and chemistry teacher. His interests first focused on muon G2 experiment and how the muon particle interacts with magnetic fields. Currently, his main experimental effort is on the deep underground neutrino experiment, many call it DUNE, which sends neutrinos from Fermi Lab to South Dakota. And I'm very pleased to welcome Dr. Eads. Would you like to begin?
Absolutely. Thank you very much for the introduction, Judy, and thanks to everyone who's come. So again, I noticed a few familiar names in the list. So some colleagues, some family, and some former students. So hopefully you can see my screen okay. All right, so Jahred and I are going to talk a little bit about the physics of the Summer Olympics. And I'm going to start things off. So again, well, Judy gave me a nice introduction, but again, just a little bit more about me. So I'm a physics professor here at
Mike,
NIU.
we don't actually see your slides, so technical glitch.
I bet that's because I didn't actually share my screen.
Again, science is hard, everybody.
Yeah, science is hard. Okay. All right, so hopefully now you can see things.
Yeah.
All right. Thank you very much. Okay. See, this is one of the things as a professor, when you make a mistake, you say, oh, I was just seeing if you guys were paying attention. So Okay, so that was your first test. All right, and at least Jahred passed. Okay, so physics of the Summer Olympics. All right, so again, I'm an NIU physics professor. So again, if you want to see a very interesting and exciting series of short videos on the physics of football, there's a little YouTube link down there. As Judy mentioned, I'm an experimental particle physicist. So which means I understand I try to understand the fundamental particles that make up the universe and the forces that they interact with. And again, when I started at NIU, I was mostly working on this muon G-2 experiment. And currently I'm working on Dune, which is currently in the planning and design stages, but eventually it's going to send a beam of neutrinos 800 miles underground from Fermilab to South Dakota. I'm a lifelong football fan, and I'm also an avid runner, and I've been getting into some other endurance type events. And yes, as it turns out, I think I have never actually taken a decent finish line photo. So I always end up looking very strange. Okay, but that's the way it goes. All right, so what exactly is physics? So, and we have a little poll. So Becky, if you could put up the first poll. So first question, just to get a little background on our audience. So first, have you ever taken a physics class before? Yes or no? And this could be any level, high school, college, whatever. And if you took a physics class, did you enjoy it? So I'll give you, a few seconds to answer the poll. Hopefully it's popping up on your screen. All right, and Becky, actually, I don't see anywhere how many people have responded. So I will leave it up to you when a fair number have responded, or again, give it, I don't know, 10, 15 more seconds if you want to then close it and show the results. Okay, so the results. Ooh, so 87% of us have taken a physics class before, which I'm very encouraged by. That's actually well, that tells me that there's more people in this audience that have taken physics than sort of if you were just to take a random section of people, there are more people in this audience have taken physics than is typical. And it's kind of, so about 2/3 of you did enjoy physics and about 1/3 of you did not, which, yeah, that's another interesting thing. Since I run the physics and chemistry teaching program for people who want to be future high school and science teachers, I ask people this question a lot, and it seems interesting that especially in physics, when people took physics, they either loved it or they hated it, and there tends not to be a lot of middle ground. All right, so most of you then, or 87% of you, should have some idea of what physics is, but physics is all about the study of matter and energy. And of course, well, matter and energy is like everything in the universe. So in a sense, it's the study of everything. And the way I like to think about it, the goal of physics is really to provide an understanding of the physical world we live in. And well, it's an experimental science, which means we develop theories based on experiments, right? So we design experiments and we take data, and then based on that, we develop theories, and then we go out and design experiments to test those theories and so on. And again, the goal is really to understand the world around us. And well, people are sometimes scared of physics. Now, I would argue they shouldn't be. But part of the reason I think is because physics has a reputation of being rather math heavy. But I think it's important to remember, yes, math is a useful tool, but physics is more than math, right? It's not just math, it's really understanding how things work. And one of the central parts of physics is studying moving objects. And of course, Olympic events involve a lot of moving objects. All right, so I have a little video here, and this is, well, rather famous video. So this is Usain Bolt. So this is the 100-meter this was the 2009 World Championships in Berlin, and this is his world record run. So he is in lane 4, and you will rather quickly see him distance himself from everybody else. All right, So he was a moving object. So when we're thinking about moving objects, how do we describe motion? So again, this is one of the central things in physics, how we describe motion. And to do that, we're gonna have to define a few terms. So one of the important things to talk about is something we call speed, right? And this is a pretty common term. And speed is really just how far did an object travel divided by how long it took. So it's a distance divided by a time. So when you talk about speeds, typically you do that in, say, feet per second, or meters per second, or miles per hour, or kilometers per hour, or something like that. So it's a distance divided by a time. Now, in physics, we distinguish between speed and velocity because oftentimes in physics, the directions are very important. So velocity is one of those things. So velocity is the speed, so how fast, and a direction. Then we talk about acceleration. So acceleration is all about a change in velocity. So if your velocity is changing, you take that change in velocity, divide by how long it took, so the time it took to change your velocity, and that defines your acceleration. And then finally, the other important quantity is something called a force. And a force is really just a push or a pull. And again, force is another one of these things where the direction really does matter. And well, it's because a force, well, pushing one way is different than pushing another way. All right, so another interesting thing we can ask is, what about the length of the race? So we just saw Usain Bolt set a world record in the 100-meter dash. So what I have here is, these are some numbers. So these are some distances and some times. So this was a 100-meter run. He did it in 9.58 seconds. So again, this was back in 2009. So if we look at the speed, again, we just take that distance, 100 meters, divide by the time it took, 9.58 seconds. We get his speed of 10.44 meters per second. Now, we can also look at the world record for the 200 meters men's event. And again, if we take 200 meters, and again, Usain Bolt is also the world record holder in the 200 meters, and his time there was 19.19 seconds. And interestingly, well, if you look at his speed during that 200-meter run, it is nearly identical to what he ran in the 100 meters, so 10.42 meters per second. Now, things start to get more interesting as we go to other races. So, for example, the 400-meter. So, Wade Van Niekerk is the world record holder there in 43.03 seconds. And if we take 400 meters divided by 43.03 seconds, his average speed was only 9.30 meters per second. So he was slower than Usain Bolt in the 100 and 200 meter world records. And then going even longer, so the 800 meter men's world record was David Rudisha. And again, his average speed was 7.93 meters per second. And then finally, the last one I listed here is the 10K. And this was Joshua Cheptegei. And his average speed during this 10K world record was only 6.37 meters per second. Well, I say only, but yeah, that's much faster than I could run a 10K. Okay, so it's sort of interesting to note then, so when you start to think about the length of the race, right, and it's not just, right, running as fast as you can for a longer distance, right? Since these average speeds are starting to get much, much less, there must be something else happening here. And in fact, another way we could think about motion is to remember, so there's different ways you can think about speed. So what I've done here is actually calculate an average speed. So I took the total distance traveled divided by the total time it took, and that defines our average speed. But there's also something we can think about called an instantaneous speed. So imagine if you had a police officer with a little radar gun, and he was actually measuring the speed at specific instances during these races. So that's the instantaneous speed, the speed at a given instant. And in fact, we can actually look at, so they have a lot of these races, they actually collect data at various intervals. So we can actually measure something close to what these instantaneous speeds are. So this is actually from an article in the American Journal of Physics. And the plot's a little busy, so let's highlight some different races here. So, and the horizontal axis here is what's called the normalized time. So the way to think about this is at the left hand of the scale here, that's the start of the race. The right hand of the scale at 1.0, that's the end of the race. And again, since each of these, it's plotting races of different lengths, they're all sort of squished to be on the same scale. So again, one side is the beginning, one side is the end. So like the middle 0.5 would be halfway through the race. All right, so now the 100 meters. So that's highlighted here in red. So, and in red, so again, this was Usain Bolt. And what you'll notice is, well, you can actually see, of course, if you, well, the video we just watched. So he starts off at rest. So he actually starts off with a speed of 0. And he has to accelerate. And in the 100 meters, you can very clearly see this acceleration, right? So his speed is increasing and increasing and increasing. He pretty much levels off at some point, and then he travels at that maximum speed for the rest of the way. And his maximum speed, you can see here, is actually close to around 12 meters per second, right? Which is faster than his average speed, right? Because he had to spend some of this time actually accelerating up to that full speed. Now things start to get interesting once you start to look at longer races. So in particular, the 400 meters. So again, left-hand side is the beginning of the race, right-hand side is the end of the race. And for the 400 meters, you can see, well, again, there's some period where, right, so again, you start off at rest. So he has to speed up. But then what you actually see is that unlike the 100 meters, his speed actually starts to taper off towards the end. So he's not actually able to maintain that top speed the whole time, and it actually starts to slow down near the end. And then again, if you look at the 10,000 meters, so now this is like a 6-mile run. And again, well, on this, he's still accelerating at the beginning, but now since we're squeezing much more distance into the same plot, you don't actually notice the scale is just too small. You don't even notice the acceleration at the beginning, but it's actually the speed throughout is pretty constant. So it's almost the same speed all the way throughout the race. And this actually has a lot to do with the way the human body works. So if you've ever had a biology class, well, since most of you have taken physics, I would probably guess that most of you have taken biology. And when it comes to biology, there's different ways that your cells can actually make energy. And there's anaerobic respiration and aerobic respiration. And these different races and how fast you can run in different races actually has a lot to do with these different types of respiration. So for something short, like a 100 or 200 meter dash, you can actually rely on anaerobic respiration for most of that. But for the longer races, especially once you hit a mile or more, you actually have to rely on aerobic respiration, which means you actually, the top speeds you get are actually much, much less. All right, so, and another question you can ask is, how do runners get moving? And so this is going to bring us into, well, start our discussion of Mr. Isaac Newton. So Becky, I think I actually missed one poll. So if you can pull up the poll for slide 7, hopefully. That's not going to miss. Yep. Okay, very good. So next poll question. So again, if you've had physics, you may remember Mr. Isaac Newton. And so the poll question for you is, how many laws does Mr. Newton have? So was it 2? Was it 3? Was it 4? Or was it 5? So I'll give you a few seconds to answer. All right, so, and thank you for pulling it up. Right, oh, so very good. So most of you remembered that, yes, there are 3 Newton's laws. All right, so let's talk just briefly about Newton's laws. So first off, well, as we mentioned, so in a race, so the runner starts off at rest. So in the picture here, so this is actually the US Olympic trials about a month ago, and this is the women's 200 event. So the sprinters start in their blocks at rest. So then at some point, right, the gun goes off and they exert a force causing their body to move forward, right? So they go from rest and then they're moving, right? And they accelerate up to, as we saw in the previous slide, they accelerate up to some top speed. And it's also kind of interesting, these blocks here are actually designed to sort of optimize that force, right? So the angles that their legs are at are actually, it's a better angle so they can exert more force with their legs so they get a larger acceleration or a larger force, which produces a larger acceleration. So these sprinters or any runners, they start with a speed of 0 and then they quickly accelerate up to full speed. And this is actually a nice illustration of Mr. Newton's first law. So there's a couple ways you can state Newton's first law. So one way is to say that an object at rest stays at rest and an object in motion stays in motion at a constant speed in a straight line unless acted on by an external force. So if we have our sprinters at rest and well, if they're going to start moving, then there must be a force. Or another way we can state Newton's first law is to say that every object in a uniform state of motion tends to remain in that state of motion until an external force is applied to it. All right, so this is actually sort of something interesting to think about and something that if you're new to physics, you may struggle with, because it's always, you have to remember there's lots of things like friction and air resistance that oppose motion, and these things are actually producing forces, right? So if you have an object and you try to slide a book or something across your desk, well, it doesn't stay in motion, it actually will come to a stop. And the reason for that is because there's friction, right? So there's friction and that opposes the motion, it exerts a force and it causes it to slow down. And it's also important to remember that there is friction in the joints of your body. I think as we get older, we get more friction in the various joints of our body. And also another interesting thing to think about is just the way that humans move, right? To actually stay moving, or if you imagine, Usain Bolt running down the track, the human body actually you have to move your arms and legs back and forth. So again, that requires force. Okay, which actually interesting to think about, and there's actually a lot of people have done research on the runner's gait. So how exactly do runners run, and what's the optimal way to do that? Now in physics, about the only thing we know how to deal with is something called a rigid body, right? So a rigid body is just some object that doesn't deform, right? So it's solid and stable. So, and you take rigid bodies and you connect various rigid bodies with various springs and things, and you use that to build up a model of something like a person, right? A human body is a pretty complicated thing. So there is actually this paper in the Journal of Experimental Biology, and this on the left here, so under A, so this is their actual model of a runner. So the M's, so they have various masses. So most of that is actually they use the mass of the lower leg and then the mass of the main body. They connected these masses with various springs. So these K's are various springs, and then they also have dampers in here. So this is kind of like a shock absorber. And you connect a bunch of these in rather complicated ways, and this is their model of a running person. And well, it looks complicated, but in terms of the physics, this is actually something we can analyze because we know how masses and springs and dampers all work. And what they actually did is they used this to predict what the force on the ground was going to be. And then they actually put runners on treadmills with little sensors in their shoes, and they actually measured those forces, and it actually compared quite well. So this actually seems to be a pretty good model. But one of the interesting things that I found is they actually did some comparisons of distance runners versus sprinters. And they actually found there was some noticeable differences between the two. So for example, if you look at sprinters, so like Usain Bolt running the 100 meters or the 200 meters. So sprinters, and when you're running fast, you actually hit the ground with a lot more force, which is actually perhaps not so surprising, right? Because if you're going to run a marathon and, be out there for several hours, right? So that's your feet are hitting the ground a lot of times, right? So you do actually want to minimize that force and minimize those impacts. Another interesting thing is that when you look at these different gaits, so when you look at distance runners versus sprinters, the distance runners actually show a lot less up and down motion in their body. So again, we didn't look at it in slow motion, but if you look at a slow motion video of a sprinter, you'll see their entire body moves up and down by a fair amount. Whereas if you look at a marathoner or a distance runner, that the the average position of their body stays pretty level. And there's actually also good reasons for that. And that gets into energy and sort of minimizing the amount of work and energy, which Jahred is going to talk about shortly. Okay, so now another interesting question you could think about is, why are runners different sizes? So for example, so this picture, so this is Noah Lyles, so, and Carrie and Knighton right here. So again, this was at the US Olympic trials. So both of these gentlemen are going to go to the Olympics in Tokyo to run the 200 meters for Team USA. So Noah Lyles, he's 5'11" and 154 pounds. Now you compare that with Galen Rupp. So he's actually also on Team USA. He's going to be running the marathon. I think this picture though is actually from the 10K from the 2012 London Olympics. But Galen Rupp, he's 5'11", so he's the same height, but he's only 135 pounds. So the difference is actually he's 20 pounds lighter. So I guess, well, you would definitely say he's thin. Noah Lyles, well, he's probably, well, depending on who you're comparing to, you may or may not think he's thin, but he's not nearly as thin as Galen Rupp. And you could ask the question, well, why is that? And there are actually very good physics reasons for that. And again, if we go back to this plot, so remember, if you're a sprinter, actually this acceleration is very, very important, right? Because the race is pretty short. So the quicker that you can accelerate up to full speed, then the quicker you're going to run the race as a whole. So what that means is it's actually better to have a larger acceleration, and to get a larger acceleration, well, you need bigger muscles. So sprinters tend to have a lot more mass. And again, if you've looked at these world-class sprinters, I mean, their legs are just massive. So they have very large, very strong legs, so they can exert very large forces, so they can accelerate very quickly. On the other hand, if you look at distance races, like the 10K or the marathon, that initial acceleration is not important at all, right? So it's just such a teeny fraction of the whole entire race that it actually doesn't really matter. So for the distance races, it's actually much more important because, well, the more mass you have, then the more work you have to do to actually keep going for that, 6 miles or 26 miles or however long it is. So it's actually, you're better off to actually be much thinner and much lighter. That's just less mass that you have to move. All right, which brings us to Newton's second law, which tells us about mass and acceleration and forces. And the key thing is that the acceleration is indirectly proportional to the mass and directly proportional to the vector sum of the forces. So the more force on the same amount of mass, you get more acceleration. Okay, so now here's another, well, here's a very cool video. Again, this was from the 2012 Olympics. So this is the US women's soccer team. So this was Canada versus USA. So, and this is Megan Rapinoe in a corner kick. So it's a little hard to see in the video since it's zoomed way out, but actually Megan Rapinoe, she's down here in the corner. You can kind of see her as this dark spot. The ball is sitting here. It's a corner kick. So it went out of bounds on this end line. And so now she's kicking it back in. And of course, here's the goal. And we can look to see what's going to happen. All right, so that was pretty quick. We're going to see a slow motion recap from a little bit different angle. Oh, which is not what I wanted to do. Okay, so, and you can see here, so the ball, all right, so we're going backwards. So here, the ball is traveling sort of down this line. And then you can see the ball kind of takes a left turn and goes right in the goal. So, and again, this is a rather unusual thing in soccer. So, and my understanding is this is the only time it's ever happened in the Olympics. So it doesn't happen very often to actually score directly on a corner kick like this. Okay, so was Newton wrong? So, so we've got, so Becky, if you could pull up the poll for slide 14. So we saw the soccer ball curved in the air. Now, according to Mr. Newton in his first law, well, objects in motion should stay in motion in straight lines. So that didn't look like a straight line to me. So was Newton wrong? Was there a force pushing it in that direction? Or, I don't know, that's why I came to the talk. So I'll give you a couple of questions to answer the poll, or a couple of seconds to answer the poll. All right, so thank you, Becky. Wow, so you guys are good. The 91%. So yes, there is a force pushing it in that direction. So exactly right. So Newton's first law says objects in motion stay in motion in straight lines. Well, that wasn't a straight line. And in fact, this little diagram here, so this is sort of the top view of the soccer pitch. So the ball started off in this corner area. So again, if you're going to kick it, well, it's going to travel in a straight line. Well, it's going to go up and down because there's a force of gravity, but from a top view, you would expect it to travel in a straight line since it's a moving object, but that's not what happened, right? So what we saw is instead more like the yellow here is that the ball actually sort of curved off to the left. So if we believe in Isaac Newton, then there must have been some sort of a force. So, and to understand where this force came from, we have to know a little bit about aerodynamics. So the ball's traveling through the air, so it's not traveling through a vacuum. And of course, there are forces when things travel through air, right? If you don't believe me, well, the next time you're driving in your car, and if you're traveling at, 55 miles an hour, stick your hand out the window and you'll feel a force. So the air does exert a force. Now, however, the interesting thing, so if the ball is spinning, and if you were watching that video carefully, the ball was definitely spinning. So what happens when the ball is spinning, or when you have a spinning object moving through the air, and this diagram here, so imagine this is like a top view. So you're looking down on this ball. So the ball is spinning clockwise. What happens is you actually get a difference in pressure due to this spinning and how the ball interacts with the air as it goes around it. And what happens is there's a difference in pressure. So you end up with a high pressure, well, the way that's spinning, you get a high pressure on the bottom here, a low pressure on the top. So that actually creates a force pointing upward. So it gets a force. So the spinning can actually cause one of these lateral forces that can cause balls to bend. And this is known as the Magnus Force. So here's another little nifty little animation. So what we can see, so first off, we've got a round object, and this is in a air tunnel. So if it's not spinning, you see it just kind of cuts through the air. But as soon as this thing starts to spin, so now it is spinning, so you can see the air is actually bent, and we wind up with a net force. So this is the Magnus Force, and this is actually why Megan Rapinoe was able to score on this corner kick. So she had just the right spin on the ball, which created a force which actually bent it just enough to get into the goal. And this Magnus Force gets used all the time, well, pretty much anything with a ball. So in baseball, right, so this is how a curve ball works, in, baseball, golf, tennis, right? Any time where you have ball spinning in the air, you can use this effect. All right, so let's go to the pool. So this is, again, the Olympic trials, the 10-meter platform. So this is Katrina Young, who is, again, will be representing the US in Tokyo. And she takes a couple of steps and off she goes into the pool. And we're gonna watch that a little slower. All right, so if we pause it right here. So if you notice, right before she leaves the platform, she actually, her body goes up. So if I can freeze it again here, right there. So you see her body actually went up a little bit. So Becky, if you could put up the poll for slide 16. So the question for you is, why did she move upward? So was it the force from her legs that caused her to move upward? Was it the force from the platform? Or, I don't know, that's why I came to the talk. So I'll give you a couple of questions or a couple of seconds to answer. So the force from her legs. Okay, so this is, what people would often say, however, this is an interesting illustration of what's called Newton's third law. So here we can see her frozen right here. You can definitely see her legs bent, right? So she is exerting a force with her legs. However, she's pushing down on the platform with her legs. So it's the force she's exerting with her legs is down. However, we saw she moved up, right? So her body moved up. So in order for her body to move up, there must have been a force pointing up. And in fact, there was. So she exerted a force down on the platform. And it turns out the platform exerts a force back up on her. So it's actually the force from the platform that causes her body to move up. And that's exactly what we get from Newton's third law. So, and again, sort of the common way to say it is that for every action, there's an equal and opposite reaction, but I don't like that version so much since it doesn't help if you don't know what an action and reaction are. So they're just forces. So the better way, which, well, it's wordier, but it's more precise. So when one body exerts a force on a second body, the second body simultaneously exerts a force equal in magnitude and opposite in direction on the first body. So she pushes down on the platform pushes up on her. And that's actually, it's that force from the platform that actually causes her body to move upward. And finally, let's also think just a little bit about rotation. So this is Jessica Parado. And again, this is the US Olympic trials again. And again, another platform dive. She jumps, she tucks, and then she's into the water. And we'll look at that again real quick. All right, so here we see again, she's pushing down on the floor. She's pushing down on the platform. The platform is pushing up on her. So if we look at the forces on her in this sort of image here, so the platform is exerting a force up on her feet. Now gravity, she has a mass and gravity pulls everything down. She's also experiencing a force due to gravity. So if you think about the forces on her body, she's got a force up on her feet, a force down on her, well, her center of gravity. So that actually causes her body to start to twist. And in physics, this combination of forces is known as a torque. So a torque is actually what causes her to rotate. Now, the other interesting thing to note, so once she leaves the platform, you'll notice, we'll go back to the video here. And we'll fast forward. So notice she tucks, she rotates, and then also notice as she gets close to the water, she lays out. And it's actually Dr. Adelman will talk more about exactly why that is. Okay, so again, please submit questions to the Q&A. So as Judy mentioned right at the beginning, we're happy to answer questions. And on to part 2. Okay, good. And things are happening, which means I haven't been talking to myself.
No, you haven't been. I think we're waiting for Judy, but I can go ahead if... Judy, are you there?
I'm here. Thank you for your patience. All right. Thank you very much, Dr. Eads. Our second speaker is Dr. Jahred Adelman. Dr. Adelman says that thinking about sports from the perspective of a physicist can lead to surprising insights. The physical laws of describing everything taking place in Tokyo 2021 are no different from those that explain everyday life, from driving a car to walking to work to taking the train. People may not know it, but they are already physicists. We all intuitively understand and use Newton's laws without even realizing it. So I would like you to know that Dr. Adelman is an NIU Associate Professor in the Department of Physics. He is a Director of Northern Illinois Center for Accelerator and Detector Development. He is also Director of Graduate Studies. He holds a PhD from the University of Chicago and an SCB from Brown University. His research interests include elementary particle physics, Higgs boson physics, top quark physics and connection to the Higgs boson, hardware-based track triggers, and physics of sports. I'm pleased to welcome Dr. Edelman. Would you like to begin?
Sure. All right. So let me start up my video, and hopefully you'll be able to see my desktop. So 1 second. So people can tell me if they're actually seeing slides. Someone comment?
Yep, looks good.
Perfect. All right. So thanks, Judy, for that, and thanks everyone for coming. So since we're sort of at an intermission, and this, as Judy mentioned, really is supposed to take place in a restaurant or bar of this sort of establishment. If you are over 21, I would like to toast you with my STEM outreach glass. Cheers. This is supposed to be a sort of lighthearted event. And if you're under 21, I hope you have something tasty for dessert tonight after dinner. I hope I can follow up on Mike's excellent talk. Just sort of introduction, a little bit about me. As Judy said, I'm a particle physicist. So we, like Mike, we smash things together and try to understand what happens in the most basic building blocks of the universe, of nature, everything around us. So I wanted to sort of set the scale for my day job in context. So we try and study the tiniest things that you can imagine. And so we're studying quarks, which are really, really tiny and are inside of protons and neutrons that make up atoms themselves. And even an atom is 10 to the minus 8 centimeters across. And so if you're not used to seeing this sort of scientific notation, at 0 point, you got to start to count 0, 0, 0, 0, 0, 0, 0, 1, where 1 is in the 8th position after the decimal point. So pretty tiny. And that compares to the things we're talking about today, like basketballs, which are on the order of, roughly a meter across. Even if not that big, that's the order of magnitude, rough size. So typically I'm studying things much smaller than this. So we're going to move away from Isaac Newton. In case you didn't know, he was rooting for the US to have as many gold medals as possible. And we're going to study some things in this part of the talk that look a bit different, but in fact give you the same answers, or they should give you the same answers as Newton's 3 laws of motion. And these are conserved quantities. So if you're not familiar with this idea, it may be confusing to you or strange. Conserved quantity, what do I mean? And so to study it, we need to go back to about 100 years to a brilliant mathematical physicist, Emmy Noether. And Einstein referred to her as, if I get it right, a mathematical genius. So I'm probably missing an adjective in there, but something like a mathematical genius. So if Einstein was saying that about her, she really was, something of a genius. And she tells us that if you write down some physical theory, and we're not going to write down lots of physical theories, but if you did that and there's some symmetries in that theory, it means something is conserved. So what does it mean for something to be conserved? It means something doesn't change. Okay, so that's hopefully a concept you can wrap your head around. Just something doesn't change. So then the question is, what sort of symmetries are we talking about, right? What in the world do I mean? So the most famous symmetry that you might study from Emmy's ideas is time symmetry. And this has a very special thing in physics. And I don't mean that, 2022 next year is hopefully going to be much better than this year, which I think on average is a lot better than last year, at least for those of us in the US. That's not what we mean. By time symmetry, we mean that the laws of physics don't change at different moments of time. Now, that doesn't mean at all that what you get out of those physical laws doesn't change, right? If I throw a ball in the air and I look at what happens, at one point it's high up in the air and another point it's down on the ground. So something has changed. But the laws that you write down on paper don't depend on whether you're evaluating the ball's motion at 6 o'clock or 7 o'clock or 8 o'clock. And so Emmy Noether tells us that if you have a theory which doesn't depend on time like that, energy is conserved. Okay, so we're going to begin our discussion now with the idea that energy is conserved. And energy can take a bunch of different forms. You can start with one form of energy and end up with another form. You can go back to that first form. You can go to a third form. But you can't have energy magically disappearing into the ether. And you can't just magically create it out of nothing. Okay, so here is a gentleman that you've seen before many times probably, and also even just 20 minutes ago from Mike's talk, right? You know who this is, Usain Bolt, right? And you watch him, and you don't need to have taken many physics courses to know that he has a tremendous amount of energy. You can see him sort of taking the lead here. And this is what we refer to as kinetic energy. So this is his energy due to the fact that he is moving. Okay, now, just the fact that he's moving, that's great. That doesn't help us understand what's happening from the ideas of conservation of energy. To do that, we need to introduce at least one other type of energy. So the second type we're going to introduce is gravitational potential energy. So this is energy that's stored, and it's stored due to its position. And for the purposes of everything happening on the Olympic field, the position we're interested in is the height above the Earth. Okay, so you can have energy stored when you throw a ball up as it goes higher and higher and higher. When it reaches the top of its motion, a lot of its energy is stored, and it can then be converted when it comes back down, all right, as it starts moving again. So the total energy is always constant, it's always conserved, but each type can go back and forth between one another. So here is a fantastic example. This is Ryan Krauser. And if you don't know who he is, you should, because he just set the world's medal for the shot put, okay? And what you're going to see in this video is that he is going to be moving very, very fast. And he's going to have a tremendous amount of kinetic energy. That kinetic energy then goes into the ball, which begins moving very, very fast as well. But it slows down as it reaches higher, goes higher and higher and higher, because its kinetic energy gets converted to kinetic energy. So its kinetic energy gets converted to potential energy. And then after it reaches the top of its motion, it falls back down again. And that potential energy, you might say, gets released back to kinetic energy. Now, if there's any of you out there who are a younger kid, I want to watch this video again and tell you what not to do in real life, in case you were curious. This video is amazing. Don't ever stand 2 feet away from a man who's spinning around with a heavy metal ball, a shot put. It's a really terrible idea. And why is it a terrible idea? Because he is spinning around and the ball is spinning around with a tremendous amount of kinetic energy. And if that ball happens to go in the wrong direction, all of that energy is going to go into your face or your body and cause serious damage, right? Thankfully, he doesn't, and maybe because he's the world, world record holder, you trust him, but I'm not sure that I would. Okay, so here is another great example of gravitational potential energy. This is Eric Kennard, and he actually won the silver medal in the Olympics some number of years ago. And not that long ago, it was actually changed to a gold medal. There was a big doping scandal with Russia, and the Russian in the competition actually had the gold medal, and it was given up, and so his silver got turned to a gold. You're going to watch here, he's going to be running and have kinetic energy as he's running. That kinetic energy gets converted to potential energy as he goes up, and then released back down again as kinetic energy. Now here's already one very interesting insight. If you've ever seen anyone doing the high jump before, you may have noticed that they do it in this very strange way. They jump right backwards, and they sort of put their arms and legs around sort of this funny sort of position. And this sort of strange position is called the Fosbury flop, okay? And the reason for this is that gravitational potential energy just depends on the average position of your body. So when your high jumper is running, they have some energy, and they're going to convert that to gravitational potential energy when they jump up. But their maximum height is given by the amount of kinetic energy they have. They can't jump any higher than that. So they want to minimize the gravitational potential energy that they need to get over the bar, okay? And to do that, they want to lower the average position as much as possible to still get over the bar. And so if you jump in this sort of funny way where your legs and arms are sort of, I can't even quite do it, folded backwards like that, the average position of your body can actually be not on your body, but you can sort of see, and somehow my cursor doesn't work, but that's okay. You can sort of see that it's below the person in this sort of picture over there. So this lowers the average position, it lowers the average energy you need to cross the bar. Now, this is called the Fosbury flop after Dick Fosbury, who first did this in competition in the Olympics in 1968 in Mexico City. And if you Google all the other people who used to do the high jump before him, they had all these very, very funny scissor kicks and contortionists. They looked like they were going to like stretch their body in very strange ways to get over the bar without actually hitting it. And he was an engineer who presumably had taken some physics courses and realized that this was a better way to do this. And he won the gold medal in Mexico City because of this. And in fact, the other great thing is that you can look and see that when he did this, this is a picture of him, he had different color sneakers on. I don't know exactly why, maybe he couldn't find his the matching pair of shoes. Now, why do jumpers jump backwards? Well, that's just physiology. Your legs naturally bend that way. So if you want to have this sort of inverted U position, you can't really jump forwards. You have to jump backwards. Okay, the third type of energy we're going to talk about is spring potential energy. So you may have seen this just from like Slinkies, right? And so this is energy that's stored again due to stretching something or compressing it. And again, total energy, still constant, still conserved, but it can go back and forth between different types. So here we have another diver. So this is Cao Yuan. And what you're going to see here is that he is going to be jumping up and down off the platform, right? And there's three different types of energy that are in play here. And somehow my cursor is not working. Oh, now somehow it appeared. So we can watch when he starts diving. Look at the diving board when he, right? It is bent, right? So not only does he have some gravitational potential energy because he's above the pool, and then he's moving, so he periodically has some kinetic energy, but he's actually creating stored energy in that diving platform itself. And so this helps him jump even higher than he would be able to normally. And then of course he reaches his maximum height, and his maximum height, all his energy is completely gravitational potential energy. Right up here, he's completely got almost all his energy gravitational potential energy, and then it gets converted to kinetic energy as he moves downwards. Here's another great example. This is Sandy Morris. She's an Olympic medalist pole vaulter. She's actually originally from Downers Grove. So for those of you connecting from the NIU area, not too far away. And you can see here that she has some kinetic energy when she's running. And then her pole, whoops, that didn't work. Let's try again. Her pole bends. Right? And so a lot of her energy is now converted to this spring or elastic energy. And then it gets converted to gravitational potential energy as she goes up, and then she falls down. And as she falls, it's all converted back to kinetic energy again. So that being said, we said that energy is always conserved. You can't create it, you can't destroy it. But sometimes it seems like, if you're taking a physics course, it sometimes seems like energy is not conserved. And the question is, where did it go? And it didn't disappear magically. It just went somewhere that's hard to get back. And so it didn't go to a form of potential energy. It instead went to thermal energy for something like, for example, friction. So if you heat something up due to friction, it's hard to get that energy back. So this is the in Rio. This is the women's 8 race, and the U.S. team actually took the gold. And we'll talk about this in a few slides. What I want you to focus on is what happens when the teams slow down, right? As they're slowing down, they put their paddles in the water and they rapidly slow down, right? You can see the paddles are in the water here and they slow down a lot. So what's happening, energy hasn't disappeared. It's just that you're tiny bit, you're heating up the water a tiny bit, and that's where the energy has gone to instead. So I'd like to pause and take a break. There's with this sort of sidebar, which I think is fantastic, as I sip my beer. So cheers to everyone. So there's this story from Michael Phelps, right, the medalist swimmer, saying that there was a myth traveling around that he used to eat 12,000 calories a day, and it wasn't true according to the autobiography. Only ate 8,000 to 10,000 calories a day, which is still absurd if you think about it. And the reason, of course, he needed that many calories is, biology and biophysics and conservation of energy. He exerted a tremendous amount of energy swimming back and forth all the time, training, building up those muscles. That energy doesn't appear magically for free. He doesn't pull it out of thin air. It comes from somewhere, his beer or probably some more nutritious food that he ate. Okay, so now we're going to get to our second conservation law. And before doing that, I want to bring up the topic of what's conserved, which is momentum. So I want to step back and remind you that momentum is one of those topics that actually has connections to everyday language, right? So we use the word momentum in everyday language, in particular for sports, right? So when I'm going to talk about momentum, I'm not talking about the physics sense of momentum. I'm not talking about when the Dream Team went on this fantastic run in 1992. And you should Google this. There's all kinds of great music from the 90s that you can sort of hear. And while I'm talking, you can hear the music maybe. We say that they had some momentum, and it has a connection to the physics quantity. They kept scoring, they kept scoring, they kept scoring. The score was moving in the same direction forwards, right? It didn't stop, right? And that's sort of what we mean by momentum in the physics sense. So to talk about momentum, we need to think a little bit about the different pieces that go into it. So the first thing is that the more mass an object has, the more momentum it has. So here you have Nate Robinson, a former Bulls player, not the Olympics, but an Olympic sport, and he's going to dunk. And for a given speed, for a given velocity, he has a certain amount of momentum. And he's not a small man if you saw him on the street, but compared to everyone else around him, right? In the NBA, he's not that big. And this compares, for example, to MJ back in his day, and perhaps even more so now if you've seen pictures of him now. The more mass an object has, the more momentum it has. So for the same speed, Jordan would have more momentum. So the second thing we want to know about momentum is that it has a direction. So when we talked about energy, there was no direction involved. The higher up something was, the more potential energy it had. But we didn't care about the direction an object was moving for conservation of energy. And that's not true for momentum. Momentum points in a direction. It points in the direction the velocity is moving. So this is Kristen Armstrong. She's a 3-time Olympic gold medalist. And her momentum is pointing in the direction she's moving. Okay, so now we get to our third important thing about momentum, which it depends on the object's speed. So objects that are moving faster have more momentum. So now a more lighthearted poll perhaps than the one Mike had. So we can ask, a reasonable question: who runs here with more momentum? And it's a little bit of a trick question. Does Usain run with more momentum? Do I run with more momentum? Or did Mike, who had better poll questions, run with more momentum? And maybe it's a little bit of a trick question, so I'll give you a few seconds to answer. Mike was just telling us that he is running for a hobby, so we can pick on him for that a little bit. So it's a little bit of a trick question. So if we look and see the results, so everyone is, I don't know who the people who picked me were, but it's a little bit of a trick question because it also depends on the speed. Now, Usain's speed, but it also depends on the mass. So I'm assuming that we actually have similar masses. Usain's might be a bit more in muscle, it might be more in something else, but it's hard to actually say for certain, right? So you need to actually know the mass and the speed of something. Okay, so let's close that poll. Somehow I can't change slides. There we go. Okay, so now we get to momentum conservation. So this comes back to Emmy, and she told us that if the laws of physics don't change at different points in space, momentum is conserved. And again, this doesn't mean that the results of applying the laws of physics don't change. What's happening in right here, what I'm in my, giving this talk is different than what's happening wherever you're sitting on your couch. But the laws that you write down don't care about where you're applying them. So momentum conservation tells us that momentum can start in one object and move to another object, but the total momentum is conserved. So this is going to be a video of Clarissa Shields. She's a two-time gold medalist boxer. And, you know, she's pummeling her opponent. What I want you to focus on is what happens when her right hook connects to her opponent's head. All right, let's pause it there. All right, so kind of a bit of a brutal punch, right? So her arm, her fist, her whole body is carrying some momentum in some direction because it's moving forward. It then connects with her opponent's head. All right, we know from what Mike told us that there's going to be some force from her opponent's head that is going to be pushing back a little bit on the boxing glove of Clarissa Shields. So it's going to be slowed down a little bit. But total momentum is conserved. So how do we get total momentum to be conserved? We can only be conserved if the head of her opponent gets pushed backwards. And not only does it get pushed backwards, we know that momentum has a direction, so it has to move in the same direction as her fist. Okay. All right. So this has a lot of different applications. So again, I'm an Olympic sport, but I had to pick this video, even though it's not the Olympics. This is something that was very controversial from a few years ago from the NBA final. So this is a video of Kevin Durant, who's driving in the paint, and you can see LeBron standing over here in the paint. And the controversy came about whether this was an offensive foul or not, which I think it got called for. But I'm not here to parse, you know, whether it was a foul or not. What I want you to see is what happens when Durant runs into James. Okay, slow motion. Watch what happens. So Durant is running towards the basket, and the minute he runs into LeBron James, there's probably two things that happen. One, LeBron probably takes a little bit of a dive, if we're being honest, but even though he's acting a little bit, he also gets pushed. And not only does he get pushed, but he gets pushed in the same direction that Durant was traveling. And that's because momentum is conserved. And if momentum is conserved, if Durant has some momentum, then and gets slowed down by coming into contact with James, some of it gets transferred to LeBron, and he then moves in that direction. You can see another great example of it right here. He gets pushed in the same direction that Durant was traveling. Okay, so now we're going to get back to our rowers, okay? And total momentum is again conserved. So this now tells us how these rowers are actually moving through the water. How are they moving through the water? Let's wait for the zoom a little bit. What they're doing is they're putting their oars in the water and they're pushing on the water, okay? And so the water is actually getting pushed to the left. And so the water is actually carrying some momentum to the left. Let's see if I can find the right moment to pause this. Right, you can see that the water is getting pushed backwards, but if the water is getting pushed backwards, it's carrying some momentum backwards. So for momentum to be conserved, the boat then has to travel in the other direction. And so that is how the rowboat keeps moving, okay? Because of momentum conservation. Okay, so the more momentum the water carries backwards, the more momentum the boat carries forwards and the faster it goes. So this then tells us something about how it is that you want to actually succeed in this Olympic sport, other than training and having the right equipment and being talented and athletic, right? If you want to think about it from a physics point of view, the more of the mass that goes backwards, the faster the boat goes forwards, because the more mass goes backwards, the more momentum gets carried backwards, and then more momentum has to be canceling that out. So the faster the boat goes forward. So this tells us, you know, if you've ever been in a canoe or a kayak or anything, and you're rowing in the lake or down a river, you want to make sure the oar is all the way in the water, right? You want to push as much water as possible. You don't want to put the oar a little bit in the water, because you're not then going to push as much water as you can. And in addition, you don't want to sort of, you know, lazily push the water. You want the water to be traveling as fast as it can backwards to provide as much momentum backwards to the water, so that when momentum is conserved, the water gets pushed forwards as much as possible. So now I want to pause and connect this to Mike's talk. And I said that conservation laws and Newton's laws really are one and the same. And this is a really good example of that. So, you know, we often talk in the intro physics classes about things like this, how you can solve physics problems in multiple ways, qualitatively or quantitatively, and you should get the same answer. So you might have one student who says, boats move because total momentum is conserved. The water goes backwards, so the boat goes forward. But if you had a student who was listening to Mike and liked, Newton's laws, that student might say the boats move because the oars apply a force to the water. And what does Newton's third law tell us? If the oars apply a force to the water, then the water applies a force back on the oars and thus the boats. And in fact, if you do this with the math itself, you also get the same answer. So now let's think about this from a different Olympic sport. So Zach Levine has actually been in the Olympics, and so he's playing for the Bulls, but he's jumping up for a dunk. And so I'm going to anticipate a question you could get in the Q&A. To conserve momentum, if Zach Levine jumps up, shouldn't the Earth move too? And so there's a few possibilities. One is no. You could say it shouldn't because the Earth is in outer space. You could say yes, it's a tiny distance. You could say yes, but actually it's not because there's always other people moving. Or maybe you can take the cop-out answer and say only if the Bulls are better next year. But this is an Olympic talk, so even though I picked some NBA things, you could guess that the last one is maybe not correct. All right. So this is a very valid question, and we're actually going to try and figure this out. So let's look at the answers first. So we had 12 of you, so most of you said it's a really tiny distance. One of you is wishing the Bulls are going to be better, and one of you picked the interesting answer, which is no, because the Earth is in outer space. So let's close that and talk for a second about that. When humans and went to send, we're talking now about many decades ago, when humans went to send astronauts and space shuttles to outer space, there were some people who said that space travel couldn't work because space is a vacuum, and so there's nothing to push against, and so you couldn't actually use rockets in outer space. And it turns out that's wrong. Okay, so sorry to the person who gave the first answer. We know that things can move in outer space, right? You can use rockets in outer space. Space shuttles can travel to Mars. They can travel to the moon and the such, right? So let's go and calculate it if we can close that poll. All right, so we're going to just put some numbers down. So the mass of Zach Levine is roughly 200 pounds. The mass of the Earth, roughly 10 to the 25th pound. So if you don't like scientific notation, this is 1 with 25 zeros after it pounds. And we're talking about approximate. When Zach Levine jumps up to dunk, he's jumping something like 6 feet up in the air. He's not jumping 30 feet. He's jumping more than 1 feet, something like 6 feet. So now if I gave this problem to students in my intro physics class, they could convert that jump height to find how fast Zach Levine jumped when he left the ground. And how could they do this? They could use conservation of energy. When he reaches the maximum height of 6 feet, all of his energy has been converted to gravitational potential energy. But that energy didn't just appear from somewhere, it started as kinetic energy. So we could convert that 6-foot jump to find how fast he was moving when he originally jumped up, and it's something like 10, 15 miles an hour. All right. So you can then take the 10, 15 miles an hour, and you can take the mass of those objects, and you find that the Earth moves away from Zach Levine with a speed. It does move away from Zach Levine when he jumps up with the speed of something like 10 to the minus 23 miles per hour, solely due to conservation of momentum. If you don't like that, it's 0.000, and I'm not going to read all the zeros, but a really, really tiny number. So the Earth actually does move away from him. Of course, there's other people moving on the Earth. That's a really tiny number, so you're never going to be able to measure this. But in fact, it does occur, which is kind of cool. Okay, so let's get to our last symmetry, the last topic of the evening, which is orientation symmetry and angular momentum. So Emmy tells us that the laws of physics don't change if you look in different directions, if you rotate. Okay, it doesn't matter what direction you're pointing in or you're looking in, the laws of physics are the same. And if that's true, angular momentum is conserved. So angular momentum, we're going to think of it as momentum for objects that are rotating. So instead of velocity, which is just how fast an object moves, we have angular velocity, which is how fast an object rotates. Okay, so you can have a frisbee that's sort of spinning around like that, and how fast it's spinning is going to tell us something about the angular momentum. But this is now the trick for angular momentum. This requires us to determine how the object was rotating, or in other words, the axis of rotation. So the Frisbee on the left, as I've sort of tried to draw this axis of rotation, it would be much easier in person for this, would be spinning sort of like you'd want to throw a Frisbee as it was rotating. On the right, that Frisbee would be rotating sort of a different way. And in fact, when it took 1/2 turn, you would see the underside of the Frisbee. And that's not how you normally throw a Frisbee. So the axis that the object is spinning is an important part of angular momentum. Okay, so here is Hannah Roberts. She's a BMX freestyle cyclist, and that's actually a new Olympic sport. And you can see here all the different axes of rotation as she is competing here, right? So she has one axis of rotation, there's another small one in her wheel. That's a different one as her bike is rotating. And you can see here she's going to go upside down, right? So this is a very different axis of rotation. She's actually going upside down, which we hadn't yet seen before. So defining the axis of rotation is critical to understanding the angular momentum. Now, the last thing that we need to know about angular momentum is that it's not just the mass that matters, that does matter, but it also depends on how far that mass is from the axis of rotation, okay? So if the mass is close to the axis of rotation or far from it or in one direction with respect to it or another, that actually changes the angular momentum. And so the angular momentum has some more directionality in some sense than the linear momentum or regular momentum that we talked about before. So this is Nathan Chen, the Olympic medalist. And conservation of angular momentum tells us that if more mass gets closer to the rotation axis, we still want to conserve angular momentum, so the rotation speeds increase. So you can see Chen here, he's going to go for a jump. And if we go back a little bit, watch what happens when he's in his jump. All his mass is really, really close to him, really close to that rotation axis about which he's spinning. And that's why he speeds up, right? He speeds up. And then I want you to watch what happens when he lands. If you've ever noticed this, when, no, I went too far. Let's see. There we go. When he lands, he actually puts his leg out. So he can't put both his legs out, or he wouldn't be on the ice anymore, but he puts his arms out and he puts one leg out. So he gets more of his mass far from the rotation axis. And why does he do that? Well, he's done with his jump and his spin. He doesn't want to keep rotating because then he'll fall. He wants to slow his rotation down. And because angular momentum is conserved, if he puts more mass away from that rotation axis, he actually slows down. Okay, so this is something that is actually discussed. These are high jumpers, free jumpers. This is actually being discussed of potentially being a summer sport in the next summer Olympics or the one after that. And so this is a great slow motion video. And you can see that this diver has some rotation axis. And watch what happens. He actually changes how he's rotating. Watch, he just stuck his arm out. And when he does that, he actually changes how he rotates. Then he tucks his arm like that, and he changes again how he rotates. And watch what he does when he is about to land. He sticks his arms out. He sticks his arms out because he wants to slow down his spin. He doesn't want to do a belly flop in the water. He wants to control how he lands. And so he slows his rotation down, controls it, and lands exactly the way he wants to, okay? So because angular momentum depends on the distance to the rotation axis and the orientation, if you change that mass distribution, you can actually change how something rotates even while conserving angular momentum. All right, so we have one last video and then I'm done for the evening, and you might maybe guess who it is because it's hard to envision a talk on the Summer Olympics in the US without, you know, the greatest Olympian in the US or the world right now, really, Simone Biles, right? And so we're going to put a lot of the concept we've learned together here in this beautiful slow motion video. Okay, so she has some already motion. I've sort of clipped the video a little bit. And she pushes off. So she applies a force to the ground with her foot, with her feet, and then with her arms. She pushes off, causing her to have some kinetic energy. That kinetic energy, though, gets converted to gravitational potential energy as she goes up and as she starts to spin, okay? And then watch what happens when she really gets higher and higher. She moves her arms and starts to rotate her arms, brings her arm in. And when she does that, she can actually change how she rotates. Now she tucks her arms in, and she's going to start rotating faster and faster. Even in the slow motion video, you can see it. She's at the maximum of her height, so as much of her energy is converted to potential energy, gravitational potential energy as possible. And watch what happens when she comes down to land. She wants to get a smooth landing. She wants to slow down her rotation as she lands, and in particular, once she lands. So she is going to put her arms straight out so that she doesn't keep rotating and spinning. And so she gets her gold medal. So I think I'll leave it at that. I hope you have fun watching the Olympics. I hope you learned a bit, and don't hesitate to ask me and to ask Mike a bunch of questions. All right.
So thank you very much, Dr. Adelman and Dr. Eads. Now we will have our Q&A, and we will give people just a few minutes to refresh their drinks and to think of some comments or some questions if they haven't done so already. And we will, in the meantime, I'm going to give you some information while we're waiting for people to think up some questions or put some information in there. By the way, if you actually would like to ask the question yourself instead of having me read the question, you can raise your hand, and they will let you ask the question, and then right after that they'll mute your mic. So feel free to do that if you would like to. So, and we will read the questions, and then you can answer. And so while we're waiting, I want you to remind you of our Next Time Cafe, which is scheduled for August 12th at 7 p.m. Stargazing, and I didn't mention earlier that I did say that we were having 2 Argonne researchers, but they are Dr. Amy Bender and Dr. Lindsay Bleem. And the topic that they are going to discuss is the beginning and end of the universe as observed from the bottom of the world. And our NASA scientists who graduated from NIU, Marco Castillo and Kristen Knudsen, they're going to talk about rovers, data, and technology, finding signs of life on Mars. And so they will be live, but virtually they will be with us. So, and as I told you, we'll probably get some of those moon rocks, so that'll be pretty exciting. I've been also asked to share information for an event that my colleague is going to be having on August 4th at 6:30. Jillian Cargile is going to have a webinar event, and it is Future Telling, Comets and Craters. Guest speakers will be the author Benjamin Percy and historian Andy Bruno. And we also want to share with you, I don't have a slide on it, but we have been invited to Springfield for the Illinois State Fair, and they are going to have a State Fair Expo, and so we will be a part of that from the 18th through the 22nd. It's in a separate building, an expo building, but we're happy to be there. It's actually going to be kind of a mini STEM fest because we'll have lots of hands-on activities that you might want to participate if you're going to be at the fair. So looks like we have some questions or some comments, so we're ready to start a discussion and probably have some people think of some things after we begin here. So, everybody ready? All right, so our first one is from Susan. I said no to number 1, and I don't know. These are comments, I guess. I don't know. And they appreciated Dr. Eads' talk. These came in very early, and here we have Katie asking a question. If the diving board didn't exert an equal force to the diver's legs, it would move, right?
Yes, thanks for that question, Katie. So the important thing to remember, right? So if you're interested in what the diving board is going to do, you need to look at all the forces on the diving board, right? So that it's not just the diver pushing down on the diving board, right? Typically, there's also like a fulcrum point, and then you got bolts or something to mount the diving board. So it's the total forces from all of those that you need to add up to determine if the diving board is going to move or not.
Thank you. I was wondering about that as well, because I thought it was actually two. I mean, the force from the legs and of the board, but you didn't give that as an option.
So just to add a little bit to that, right? The diving board, when you look at the ones where they do bend, right? You know, depending on the diving board, some of them are sort of fixed, but then there's the ones where the board does bend, and the reason it bends is because there is some force when the diver is jumping up and down and on it and landing on it, right? And the reason it doesn't bend forever is that eventually that force gets counteracted. The force from it bending gets sort of counteracted by all the other forces, right? So the more it bends, the more there's a spring force involved.
And so the next two comments were that they obviously loved your presentations, both of you, and thank you on planning on watching the Olympics. I want to tell you that I appreciated that they had the stem glass there and the toast. I think we all enjoyed that. Both of you will have another stem glass in your future, so you can have a friend in for a toast. I just need to get there to deliver them. And I really appreciated all the action shots. I mean, I think that was fun. And the variety of sports that you actually illustrated through this. I enjoyed that you also added an ice skater, since my son has been one of those ice skaters. So, maybe we should give a couple more minutes and see if somebody wants to add a comment or a question. So we don't see any other ones right now, but maybe both of you could tell us some of your takeaways. You know, what would you like the audience to take away from this? And by the way, I just wanted to comment that I thought it was interesting that now there are no spectators. Is that correct? From any nation?
So.
Yeah.
I think so. Yeah.
And to me, I think that's important because I think that, and I don't know for sure, but I think that some of these athletes actually maybe do better because they have an audience or their family's there, or somebody cheering them on. And so it didn't seem fair to me that some nations or Tokyo or whatever would get their audience and that we wouldn't. So I mean, I just think now it's a little bit more of an equal playing field. But anyway, what do you think are the main takeaways? And I don't know if our audience knows that you have talked about the physics of football, Mike, and also we've had, I don't remember if you did the physics of golf or not, but I know you did the physics of baseball, Jahred, right? So, yeah. Mm-hmm. And so we've had fun listening to you do those kinds of things. In fact, by the way, I just wanted you to know that a young man came up to me, and I don't know if I shared this with you, to tell me that he hated physics and only showed up to your event because I was going to be there, which I thought was fantastic. But he said after he left, he goes, "Do you know that if I had a professor that used sports as an example to teach physics, I would probably be a physicist today. I had so much fun, and this made so much sense to me now." We do have another comment from Lori. She said, "It seems that a lot of physics goes into the development or evolution of the equipment used by the athletes as well. The materials, the springiness of them, the safety, etc. this could be a whole nother talk. Oh, I love that. That's very true. And the equipment keeps evolving over and over, and of course it all has to be approved, but that's an interesting thing you might want to comment on.
Yeah, absolutely. And there's a lot of physics, there's a lot of engineering in both the equipment. And I mean, another really interesting thing that they can do nowadays is like just the fact that sensors and electronics are so low or so small and you can put them anywhere. I mean, I know with like football players, right? They put these sensors like all over their pads and helmets and things, and they're measuring forces like during games and practices. And I just stumbled across a interesting article. I didn't read it in detail, but so I showed one of the plots I showed in my talk, right, was that the sort of the instantaneous speeds in these races of various lengths, right? So, and that has actually been studied for a fair amount because like in these Olympic races or world championships, they have all this data for these world-class runners. But actually nowadays, this paper I saw, they were using, like fitness trackers, right? So like your Garmin or whatever. And instead of just, focusing on world-class athletes, now they can actually look at, running styles and how things change for like anybody who's a runner, right? It's not just the world-class people anymore. But yeah, I guess the one of the interesting things back when I was putting together my football physics talk, I actually found that the way they test helmets, right? So, helmets are like rated, and this actually, whether it's a football helmet or a, motorcycle helmet or whatever it is, they actually put cadaver heads in helmets and drop them onto big iron plates. There's like a specific distance that you drop it from that actually simulates an impact of, a certain speed, which, I guess there's one of those times when you read something like that and it's like, what, I'm glad I ended up in the field that I ended up in. Having to do something like that.
So, Jahred, did you have anything to comment on that?
Yeah, I mean, this is one of there's many reasons that records keep getting broken all the time. And one of them is that people train better and there's better training regimens. One of them is that people become more specialized and have money to focus on that. But one of them is also for equipment, right? So there's a lot of different reasons. So Mike and I mentioned before talking about ourselves, right? There's this big discussion about not sneakers, they're shoes or running sneakers, for running long distances, about which sort of sneakers and shoes should be allowed in races, in marathon races, right? Because, there's a question about when you run, how much of you might, discuss there's some impact that you make on the ground, right? You have some energy just from pushing back on the ground and then it pushes back on you forward. The question is, how much of that energy can you get back? So sometimes you want your shoes to be sort of springy, right? And this is always advertised. But there are limits to how well that works. There's also limits to what's allowed. And there's these new sneakers from Nike in the past few years for long distance races that are right now not legal for marathons, for example, right? And so there's, a question at some point as to what sort of equipment is allowed and what's not allowed. And that's a very big discussion, right? But as Mike said, for sure, there's engineering keeps improving, and so equipment gets better and better over time, right? And that's one of the reasons that athletes continue to break records. Fosbury coming up with a different technique is not something that happens very often, right? When someone is like, everybody has been doing this wrong, right? That is sort of more rare, right?
Yeah, and so actually, like as Jahred mentioned with the shoes and everything, so if a couple of years ago, right, they had Nike and Eliud Kipchoge, they did this, sub 2 hour marathon moonshot, right? And it was kind of a cool thing. They basically threw out the rule book and said, well, we don't care about the rules. We're just going to do everything we possibly can to actually break 2 hours in a marathon, which makes me feel kind of bad because I was like so proud of myself. I broke 2 hours and a half marathon this year, which I thought was great, but these guys are running 2 hours for a whole marathon. But yeah, I mean, they had, right, the shoes, they were like carbon fibers, so they had a little bit of a spring to them, and they had, pacers, right? So they had people so he could kind of draft off of. They were very careful where they actually ran the marathon because it was very flat and they had like the perfect weather. And yeah, so it's sort of, looking at the science and like trying to optimize everything.
I had just a comment to your question, and remember, I don't know anything about this stuff anyway. but you talked about the sensors, and they can put them in here, there, or wherever. Wouldn't they all have to be approved? Wouldn't it be unfair if somebody was wearing a sensor and somebody else not, or is that just okay?
Yeah, well, my understanding, they don't actually, and this is mostly in football where I've heard of this happening, but well, especially for the impact sensors in the helmet. And they actually, as far as I know, they don't do it in games. They just do it in practices. And again, it's just to kind of try and measure, right, since concussions have been such a big issue and really understanding, what causes concussions and how to prevent them, right? And, and it's really just a safety thing, and try to understand, well, in like a normal practice, I mean, if you're an offensive lineman, I mean, how many times does your head get hit and what kind of forces are they?
Okay.
And they do have, like, I know in soccer and things like that, sometimes they have individual players have sensors that can monitor, like, how much are they running, right? And how fast are they running, and where are they on the field? It can kind of track where people are to get an idea of, how much running do they actually do during a game.
Yeah.
So really,
it just goes not just to people, right? So we have one of our recent graduates we're very, very proud of, is my student, is now actually working for the Red Sox. And he's, as a job, right, he just analyzes data with, I tell people you can do anything with a physics degree. And he's I chat with him, he spends a lot of time analyzing how balls are hit and thrown. There's these enormous data sets that didn't used to exist because of all this technology to track how balls are thrown, how fast they get thrown, where they go, the spin on the ball, how fast balls get hit off of the bat, the angle that they get hit at. And all this stuff is only new in the past few years because of technology, and it helps teams evaluate players and their performance and who's going to do best. And it's not data on a player, but on the balls that they're throwing and hitting. But it's still really useful. So it goes along, the technology boom and big data sets along with it sort of are everywhere in science and sports, or rather in sports.
We have a couple of questions, but I just wanted to say something about that. Just listening to you guys just in the last few minutes, we've ticked off several different careers here. I mean, you can be a physics person and, be advising people about how they can perfect whatever they're doing based on the physics. And you can be a data analyst. An analytic person is a critical job for any sports. I mean, no coach can ignore analytics. So you don't have to be good at athletics, but you can certainly be involved in sports by doing that big data, as you mentioned, Jahred. And also, I forgot the third career that we talked about, but also mechanical engineering, because you're designing some of the equipment and that kind of thing. So there's a lot of different angles, a lot of different careers that we just talked about. Somebody commented that they didn't know that Fosbury was an engineer. I like the use of physics knowledge for competitive advantage. So.
Yes, I agree.
Okay, and here we have Lori asking the question or commenting. I remember that in a previous Olympics there was a big controversy over the fact that the women's vault apparatus had been set at the wrong height for some of the competitors, and this of course affected their individual performances. Was there any follow-up research on that situation?
That I do not know. I would expect that's a very psychological big impact, right?
Yeah, I don't know either. Yeah, I don't remember hearing about that. But yeah, I mean, I guess one of the things to remember, right, with these world-class athletes in sports, I mean, these are, teeny tiny differences can really make a big difference, right? So if the apparatus is an inch too high or an inch too low, right, I mean, that can definitely throw people off.
Yeah,
I can imagine. So here is a person that said, is there any evidence that Dick Fosbury actually used physics or engineering to come up with his flop?
I think I remember reading somewhere that he did use his physics knowledge. I don't remember where I read that, but I would say that you kind of have to, because no one else was doing that, and it's hard to imagine how you would come up with that without thinking about that as a physicist or an engineer, right? It just is awkward looking and was nothing like anyone else was doing, right? So So I think it really had to be somehow connected, even if not, even if he didn't didn't sit down and say, I'm going to use my degrees and my knowledge and training, right? I think at least sort of implicitly he probably did.
So Rick is asking or commenting, Dr. Edelman mentioned that in the photo of Dick Fosbury, graduate of Oregon State University in Cornwallis, he was wearing 2 different colors of shoes. I have that down as a note too.
Yeah, it's great. So I don't know where it came from, right? If it was on purpose or he couldn't find the right shoes, but apparently he was not interested. Like they were, right? This is not like we were saying. Like now their athletes are very highly trained, right? And they go to the Olympics and they like have chefs giving them every meal. Like back in the late 60s, like he went to Mexico and like he didn't even watch the rest of the games. He like went to explore some ruins, for example, right? So he wasn't even paying much attention.
One of you want to read that, or? It
sure.
says,
so go ahead, Judy.
Okay, the black or dark shoe was, in actuality, a specialized jumping shoe, while the white shoe was the standard running shoe. That's cool. Remember, Fosbury was a pioneer in this form of high jumping, and shoe technology hadn't caught up to the sport as yet. I think it also helped Fosbury to remember that he was a left-footed high jumper and always took off on his left foot. So by wearing the opposite colored shoe, it was a conscious and subconscious, whatever, reminder to jump off of his left foot. Well, that's cool.
See,
that's why we have these people in our audience to add the discussion. Very good. Thank you, Rick.
Thank you, Rick. Yeah, I did not know that. Yeah,
neither did I.
So, anybody else? I'm so glad he mentioned that, because I was going to say to you that was very observant. I mean, most people probably wouldn't have commented or noticed, but there probably was a reason. So that's cool. So let's go back to my comment about what would your takeaways be for the audience, and I'm going to give each of you a chance to give that, because we're going to get into watching the Olympics and what should we keep in mind.
Yeah, so I think for me, what I like people to take away when I give talks like this is just the idea that physics is all around us, right? And you can use physics principles to better understand all sorts of stuff, right? I mean, sometimes, if you've had a physics class, you might, get the impression that, physics is all about, a train leaves Chicago traveling at 55 miles per hour heading due east, and a train leaves Los Angeles traveling at 70 miles an hour so that sort of thing, which it is partially, but I mean, it's a lot more to it, right? And, anytime you see a moving object, right? And we saw tons of examples, whether it's running and sprinting or a high jump or, diving or whatever it is, right? I mean, what's happening, you can always see these little physics principles at work, right? And it really helps you to better understand, how these events work and exactly what the athletes are doing.
Yeah, so I would say, I mean, Mike has most of my points already, but I would add that, if you're not sitting down and taking physics and have to solve equations, a lot of the sort of mechanics and things you need to understand what's happening, in the Olympic Stadium are things you sort of intuitively understand already, right? Even if you don't realize it, right? If you want to make an object move, you've got to push on it or apply a force, right? The reason the shot the shot goes far is because he's moving very fast. If you want something to travel higher up, you have to throw it up faster, right? Or give it more energy, right? So even if people don't realize it, just from everyday experiences, they sort of understand a lot of the fundamental concepts of physics. And so if you don't have to sit and take a test in your physics class, you can actually get a really long way just from, the intuitive knowledge you already have, plus maybe some talks that might help a little bit. So there's a question about, before Fosbury, did high jumpers have to run faster to get enough energy to clear the bar? Yeah, so the flop technique does change. It's not necessarily just based on speed, but also rotating your body and this sort of thing. But the thing that stands out to me from the high jumpers before the Fosbury flop is just the contortion that they all had to do, right? Because of course the trick is not just jumping high, it's to not actually knock the bar over. You can jump really, really high if you still knock the bar over, you know, you did not succeed in that trial, right? So I think not just, you know, running faster, right? You know, it's not like runners magically, you know, don't have to run as fast or be as trained. It's that the technique is very, very, very different, is the way I would put it.
Yeah, and I think the other thing, right, before Fosbury, they just weren't able to jump as high.
Yeah.
Right. I mean, the high jump records, and you know what people are jumping today is a lot bigger, is a lot higher than it used to be before the Fosbury flop.
Well, that's interesting. We talked about that before in one of our talks with the coach and some other people for football. I think, Mike, you might have been involved in that conversation. And we talked about body mass, and just people today are much different than they were years ago. And so that is why maybe, you know, people are taller, etc. And I just stayed short. But but that means, you know, that a lot of those stats, a lot of those, you know, people are a lot bigger, and so there's a lot more physics, I mean, or things to talk about. Help me out.
Yeah, no, I remember I mean, it was, yeah, because if I remember, I think I was the one who showed that, right? And I was looking at in the NFL draft, like heights and weights and performance and various things in the NFL draft combine. And you can definitely see nowadays the football players are much more specialized, right? So you can see, if you look at, you know, tables of body weights, right, you can definitely see there's all these 300-pound, you know, offensive and defensive linemen, and, you know, where, you know, before, you know, 50 years ago, it wasn't nearly as much of a spread, right? Everybody was kind of closer to the same size, but things are much more specialized now. Yeah, and definitely, I think with like the NFL Combine, right, and we can see that, you know, the scores in various events have gotten better over the years, and I think that probably has a lot to do with the fact that people now know what they need to train for, right? So nowadays, people, if you know you're going to the NFL draft, you'll actually, you know, spend 6 months to a year training just for that.
Well, again, thank you very much. Do let me know if you know somebody that can talk about you have talked a lot about analytics today, but just a career in analytics, because I think that is something we haven't talked about. And you brought that up as really a career option, you know, related to this, you know, which we hadn't thought about too much until you mentioned it. But we definitely look forward to watching the Olympics, and because we can't be there, and this is such a different year, and things have been so confusing about whether there was going to be an audience, whether there wasn't, whether people could travel there or not. This is certainly a fix for us because it is helping us get ready for the Olympics, and I'm sure we will enjoy them much more now that we have some background knowledge, and we can look at them more critically. So I thank you again, and you have some glasses coming, by the way, in a few weeks. So anyway, I just wanted to conclude. Thank you, our audience, for joining us today. Our next STEM Cafe will be Stargazing, August 12th, 7 p.m. If you do want to get there early to get your food, you can. They will have food ready by 6:30, and they will serve from 6:30 to 8:30. But we have some terrific speakers. We actually have 5 speakers, and we probably are going to have those NASA rocks, and if weather permitting, we'll be outside and checking out the skies. And also, I want to remind you of the Future Telling webinar, Comets and Craters, that is going to be August 4th, 6:30 p.m. You can go on Anytime you want to find out what NIU STEAM is doing in our upcoming events, you can go to NIU's website and just put NIU STEAM in there, or if you're looking for STEM cafes, you can put STEM cafes in there. Remember that October 23rd is going to be our STEM Fest, and we will have STEM cafes the entire month. So we'll have 4 STEM cafes, and we also are going to have a curiosity stage, which I believe is going to be in the library because we are having STEM Fest right on campus this year. So I will have probably at least 5 talks there. So STEM Fest is for people of all ages, and we look forward to having you there. If you want to get a little bit of a taste of what STEM Fest is going to be like, you might want to go to the Illinois State Fair Czech Prairie STEM Expo, excuse me, which will go on 18th through the 22nd in Springfield, and so that might be a fun time for the family. Don't forget, we do have our survey link in the chat if you would like to give us some feedback or give us a suggestion, or you always know that you can contact me, JDYMOND at niu.edu to give us your suggestions. If you're interested in sponsoring the STEM Cafe or donating to STEMFest, the link to donate is go.niu.edu/give NIU STEAM. We really look forward to getting back in person, and so you will see that in the next couple of months we are going to have some hybrid events. Some are going to be in person, some of them are going to be virtual, so do go online and check that out. You will find this event, it has been recorded today and should be ready and on our website under STEM Cafes in the next couple of weeks. Thank you to our NIU web media and e-learning staff, Rebecca Griffith and Samantha Click. They have been behind the scenes helping us with Zoom this evening. And thank you again to our wonderful speakers, Jahred, Adelman, and Mike Eads, our professors of physics at NIU. And thank you to our sponsors, Thermo Fisher Scientific and Bayer Fund. And thank you to our audience for joining us this evening. Let us know what topics you would like to discuss in the future. Join us August 12th, 7 p.m. for stargazing in Sugar Grove at the Open Range Southwest Grill at the Bliss Creek Golf Course on August 12th. Remember, it's a Thursday, because that is going to be the evening of the peak meteor showers, Perseids meteor showers. Have a good evening.
Good night.
Yep. Thanks, everybody.
Bye-bye.
Thank you.